Hi everyone! Now that we've seen classical encryption schemes, it is high time for us to study integers more systematically and in depth in order to understand modern number-theoretic cryptographic protocols. In this first lecture, we shall investigate some interesting patterns that occur in number theory and prove them using induction. Before we do so, I would like to highlight that here we will not build integers from scratch, but writing positive integers 1, 2, 3, and 3 dots in this manner is not enough to define them. And in fact, a lot of things happen on those 3 dots here. Many of us might believe in the existence of the infinite as a religious fact, but those same 3 dots, which are meant to bridge the finite and the infinite, hide so many subtleties. We believe in the infinite, hoping that one day we won't have a contradiction or a paradox in arithmetics, the building blocks of mathematics. However, the bright Austrian mathematician Kurt Gödel surprised the community with his consistency theorems in the last century, showing that one cannot prove the consistency of arithmetics. Let us now move on to our first example and try to sum the first odd positive integers. We start with the obvious statement that 1 is equal to 1. Now if you sum 1 and 3, we find 1 plus 3 equals to 4. 1 plus 3 plus 5 is equal to 9. 1 plus 3 plus 5 plus 7 is equal to 16. And 1 plus 3 plus 5 plus 7 plus 9 is equal to 25, and so on and so forth. Interesting. We notice here that 1 is equal to 1 squared. 4 is equal to 2 squared, 9 is equal to 3 squared, 16 is 4 squared, and 25 is 5 squared. Thus, we notice from these first examples that the sum is always a perfect square. And one can conjecture that more generally, 1 plus 3 plus 5 plus 3 dots plus 2n minus 1 is equal to n squared. So the natural question is this true for every positive integer n? Is it mathematically enough to say that since things work for the first values of n, then it should be working for every value of n? Actually, we will see that we cannot confirm this unless we prove it. Moreover, one can check many more values of n to reinforce our belief in the conjecture, but this is still not enough because we cannot verify infinitely many values. In order to prove this, we will use the principle of mathematical induction and see how it works on more concrete examples. Indeed, to prove that this statement holds for every positive integer n, we will instead prove that if it holds for a given integer n, then it must hold for the integer n plus 1. But since n can be any integer, this proves that for every positive integer n, if the property holds for n, then it holds for n plus 1. From this, it follows that if the first assertion is true, then the second is also true. The second is true implies that the third is true. The third is true implies that the fourth is true, and so on and so forth. In this fashion, induction proves that our assertion is actually true for every positive integer n. In our case, suppose that for a certain integer n, we have that 1 plus 3 plus 5 plus 2n minus 1 is actually equal to n squared. And let us try to prove that we have from this 1 plus 3 plus 5 plus 2n plus 1 is equal to n plus 1 all squared. Notice here that 2n plus 1 is actually the integer, the odd integer, right after 2n minus 1. Indeed, for our certain integer n, this assertion is true, and if we add to both sides of this equality the number 2n plus 1, one gets the following identity: 1 plus 3 plus 5 plus 2n minus 1 plus again 2n plus 1 is actually equal to n squared plus 2n plus 1. And this is obviously n plus 1 all squared, which is the next square after n squared. This means that the first assertion implies actually that the second one is true. Now to conclude, we know that the conjecture is true for n equals 1. This is actually very obvious. And by mathematical induction, it must hold for n equals 2, which guarantees that it must be true for n equals 3 too. And in this fashion, our identity holds for all natural number n. Now that we're done, I would like to add a significant comment. Some of you might think that to prove our assertion, I claimed that it is true, and from this, I deduced that it is true. This is actually not true. We have never claimed the assertion true. We only assume that if it is true for a certain n, then it is true for n plus 1, which is mathematically not the same thing. I would like to show you now two more different proofs of this fact here. The first of those is one elegant geometric shape, an astonishing proof without any word. Indeed, one can draw 1 plus 3 in this fashion. So this is 1, and this is 1 plus 3. And we obviously see here that this is 2 squared. So 1 plus 3 is a perfect square, which is equal to 2 squared. If you move on now and add 5, one gets this shape here, 1 plus 2 plus 3 plus 4 and plus 5. And we see here that this is also a perfect square, which is 3 squared. Incredible, right? This illuminating geometric shape is enough to show actually that the sum of odd integers is always a perfect square. Now if we move on and add 7, one gets this shape 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, and this is again a perfect square. Now we move on to the second proof, which will be algebraic. First, notice that for every integer k, that k plus 1 all squared is equal to k squared plus 2k plus 1, and from this we deduce that k plus 1 all squared minus k squared is equal to 2k plus 1. In English, one can read this as every odd integer is actually the difference of two successive squares. From this, we derive the fact that 1 is equal to 1 squared minus 0 squared, 3 is equal to 2 squared minus 1 squared, 5 is equal to 3 squared minus 2 squared, and 7 is equal to 4 squared minus 3 squared, and so on and so forth. Now adding 1 plus 3 plus 5 plus 7 and so on and so forth is the same thing as adding 1 squared minus 0 squared plus 2 squared minus 1 squared plus 3 squared minus 2 squared plus 4 squared minus 3 squared, etc. But we notice here that we have here 1 squared minus 1 squared, we have here 2 squared minus 2 squared, 3 squared minus 3 squared, and the final result is 4 squared because actually we can get rid of 0 squared, which is equal to 0. In the same fashion, we prove that this holds for every positive integer n. Elegant, right? Let us now move on to a second pattern in number theory, in which 1 is equal to 1, and then we do 1 plus 2 plus 1, which is equal to 4, and then we have 1 plus 2 plus 3 plus 2 plus 1 is equal to 9, and then we have 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1 is equal to 16. If you keep doing this, we get 1 plus 2 plus 3 plus 4 plus 5 plus 4 again plus 3 plus 2 plus 1 is actually equal to 25, etc. Once again, we notice here that 1 is equal to 1 squared, 4 is equal to 2 squared, 9 is equal to 3 squared, 16 is 4 squared, and 25 is 5 squared. Interesting. From these examples, one could conjecture that 1 plus 2 plus 3 plus n minus 1 plus n plus again n minus 1, and going backward plus n minus 2 plus 3 plus 2 plus 1 is actually equal to n squared. And this, of course, holds for every positive integer n. To prove this, I will first show you the geometric proof, which I personally find the most elegant. Indeed, this is 1, and this is 1 plus 2, and this is 1 plus 2 plus 1 again. And we see that this is a perfect square, which is equal to 2 squared. Moving forward, now 1 plus 2 plus 3 is this is 1, and this is 1 again here, and this is 3, so this is 1 plus 2 plus 3, and now this is 1 plus 2 plus 3 plus 2 again, plus 1, in which case we see that this is actually again a perfect square, which is equal to 3 squared. Unbelievable. Now if you keep moving forward and sum until 4 and then going backward, we see that this is 1 plus 2 plus 3 plus 4, these are the 4, plus 3 again, this is 1, 2, and 3 here, plus 2, plus 1, and here we see again that we have 1 plus 2 plus 3 plus 4 plus 3 again plus 2 plus 1, which is a perfect square. I hope you see how powerful geometry is. Now we move on to prove this with induction, and suppose for a certain integer n that we have 1 plus 2 plus 3 plus n minus 1 plus n minus 1 again, and going backward, plus n minus 2 plus 3 plus 2 plus 1 is actually equal to n squared. Let me remind you that we would like to prove that this actually holds for n plus 1 as well. Indeed, in the next step, we will have to add n here and n plus 1 again, in which case we have 1 plus 2 plus 3 plus n plus 1 plus n again, and going backward, plus 3 plus 2 plus 1 is equal to n squared plus n plus 1. And this is obviously equal to n squared plus 2n plus 1, which is also equal to n plus 1 all squared. Bingo! Now we investigate a more classical number theoretical pattern. We would like to evaluate the sum s equals to 1 plus 2 plus 3 plus 4, etc. plus n. We obviously see that 1 is equal to 1, then 1 plus 2 is equal to 3, 1 plus 2 plus 3 is equal to 6, 1 plus 2 plus 3 plus 4 is equal to 10, 1 plus 2 plus 3 plus 4 plus 5 is actually equal to 10 plus 5, which is 15, etc. Now, is there any pattern here? The answer is yes, and actually 1 is equal to 1 times 1 plus 1 all divided by 2. 3 is equal to 2 times 2 plus 1 all divided by 2. 6 is equal to 3 times 3 plus 1 all divided by 2 as well. And 10 is equal to 4 times 4 plus 1 all divided by 2, and we see here that 15 is also equal to 5 times 5 plus 1 all divided by 2 as well. And I leave it for you, of course, to check these computations. These numbers are known as the triangle numbers because one can draw 1 as a dot here. 1 plus 2 is this triangle, 1 plus 2 plus 3 is this triangle here, and 1 plus 2 plus 3 plus 4 is what you see here. These are 4, these are 3, 2, and 1, and so on and so forth. We can actually see them differently. This is 1 plus 2, 1 plus 2 plus 3 here, 1 plus 2 plus 3 plus 4, and things follow the same fashion if we move forward. So the general formula is 1 plus 2 plus 3 plus 4 plus n is equal to n times n plus 1 all divided by 2. To prove this, we will first use induction, and then use algebra, and finally an elegant geometric proof. Suppose that we have for a certain integer n 1 plus 2 plus 3 plus n is equal to n times n plus 1 all divided by 2, and we would like to show that this implies that 1 plus 2 plus 3 plus n plus 1 is actually equal to n plus 1 multiplied by n plus 2 all divided by 2. Indeed, add an n plus 1 to both sides of this equality here yields 1 plus 2 plus 3 plus n plus 1 is equal to n plus 1 plus n times n plus 1 all divided by 2, which is equal to 2n plus 1 plus n times n plus 1 all divided by 2, and this is actually obviously equal to n plus 2 all times n plus 1 all divided by 2, which is the desired identity. Moreover, we have seen that our formula is true for n equals 1. This is because 1 is equal to 1 times 1 plus 1 all divided by 2, and the principle of mathematical induction proves that our formula is true for all positive integer n. The second proof is an ingenious algebraic method due to his excellence Carl Friedrich Gauss when he was only a kid. Indeed, we write the sum twice in columns in two different ways. The first way is the ascending order 1, 2, 3, 4 until n minus 1 and n, and then we write it in the descending order, which means n here, n minus 1 here, n minus 2 here, n minus 3 here, until we get here to 2 and then to 1. Now we notice if we add the numbers of each row, 1 gets here, 1 plus n is equal to n plus 1, 2 plus n minus 1 is also equal to n plus 1, 3 plus n minus 2 is also equal to n plus 1, 4 plus n minus 3 is equal to n plus 1, n minus 1 plus 2 is equal to n plus 1, and finally n plus 1 is equal to n plus 1. Let me remind you that this is our sum S and this is also our sum S. Since we have here in total n entries, this means that S plus S is equal to n times n plus 1. In which case we have 2s is equal to n times n plus 1, and we have from here that s is equal to n times n plus 1 all divided by 2. Genius, right? Yet the most elegant proof is the geometric one. Indeed, 1 is our dot here, this is 1 plus 2, this is 1 plus 2 plus 3, this is 1 plus 2 plus 3 plus the 4 here, and we have here 1 plus 2 plus 3 plus 5, etc. Now to compute our sum S, all we have to do is to complete our triangle in a rectangle in this fashion. We add here 5 dots. This is 1, 2, 3, 4, and 5. We add here 4 dots, so this is 4, 1, 2, 3, and 4. Here 3. We add here 2 dots, and we add here 1 dot. And what we get here, actually, this is probably not very obvious, but these are actually the same two triangles, and the total number of points actually is 5 here and 6 here, which is 5 times 5 plus 1. And in order to get our sum S, all we have to do is to divide by 2 here, so one gets 5 times 5 plus 1 all divided by 2, which is the desired formula. Now that we have this in pocket, one can go back to the second example and show it easily. Actually, we recognize here our sum S, and we also recognize it here. So this sum, if we denote it by t, we get that t is equal to s plus n plus 1 plus s again, which is 2s plus n plus 1. And this is actually n times n plus 1 over 2, all multiplied by 2 here, plus n plus 1, which is n times n plus 1 plus n plus 1, and this is actually equal to n plus 1 all squared, which gives the desired result. Very nice. Now one natural question one might ask, is it necessary in an induction to verify that our property holds for n equals 1? We will show here with an example that one can have the property Pn is true implies the property Pn plus 1 is true too for every positive integer n, but the property is false for every positive integer n. Indeed, that is so that if for every positive integer n we have 4 to the n is congruent to 0 modulo 3, then we must have that 4 to the n plus 1 is congruent to 0 modulo 3. We know from congruences that 4 to the n plus 1 is congruent to 4 to the n times 4 modulo 3, which gives actually 0 times 4 modulo 3, because here we suppose that 4 to the n is congruent to 0 modulo 3, and this gives us 0 modulo 3 too. Can we now confirm that for every positive integer n that 4 to the n is congruent to 0 modulo 3? Interesting. The answer is no, because 3 cannot divide any power of 4, and indeed we have that 4 is congruent itself to 1 modulo 3. We know from here that 4 squared is also congruent to 1 squared, which is congruent to 1 modulo 3, and from this one deduces that 4 to the n is in fact congruent to 1 modulo 3, which is not congruent, which means it is different from 0 modulo 3. Thus, verifying that the property holds for n equals 1 is a must in the principle of mathematical induction. Now I would like to end our lecture by a funny paradox. I will prove here by induction that any n natural numbers are equal. And I would like to highlight that this argument is due to His Excellence Alfred Tarski. Indeed, if n equals to 1, we only have one natural number and the property holds naturally. Now it remains to pass from n to n plus 1. To see how this works, let us investigate the case 3 to 4. Suppose any four numbers A, B, C, and D have been given. By assumption, the numbers A, B, and C are three numbers, so they must be equal. Likewise, the numbers B, C, and D are three numbers, so they must be equal too. From this, one concludes that the four numbers are equal. By induction, this means that any n natural numbers are actually equal. Something went wrong here. Before you see why, please take enough time to think about it. Indeed, one can pass in the same fashion from 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6, and so on and so forth. But actually the problem in this induction, that it is true for n equals 1, but there is no way to get from 1 to 2. Thus, the principle of mathematical induction does not apply, and this is wrong. Our lecture about induction and number theoretical patterns ends here, and more exciting lectures are to come. Thank you for listening.